Ladies and gentlemen, please welcome CTO Oculus, John Carmack.
All right, so I don't actually have a presentation, but I can stand up here and talk about interesting things till they run me off the stage. So, so mostly that's going to be about Gear VR, because that's what I've spent most of my effort this last year on. So for the too long didn't listen crowd, we'll start with where we are today, and then we'll go into the history and the path that took us there, which offers some insight for the current state of things. So I believe pretty strongly in being very frank and open about flaws and the limitations. So this is kind of where I go off message a little bit from the standard PR plan and talk very frankly about things. So the current killer limitations on Gear VR are the fact that it's a 60 hertz low persistence display, which has flicker problems for a lot of people, and it has no positional tracking, which is one of the critical aspects for DK2 and future products. So there are plans and mitigation strategies for what we can do around that now and how we want to improve that in the future. The 60 hertz low persistence turns out to be, it's not as tragic as a lot of people were expecting it. There were a lot of people that just like, that's completely unusable, and certainly Oculus has been talking about minimum frequencies for low persistence displays. And a lot of people were surprised that it wasn't as bad as they thought it was going to be, but there are still broad ranges of sensitivities among people, where for some people it really is bad, and some people can't even notice it. Problems with flicker sensitivity, because all the corners of the characteristic of the display screens, both on DK2, basically all of our screens that are OLED based, they have a quirk in them where they don't blur so much, but there is a 2-frame rise problem. And many of you have probably seen this, where it's a type of ghosting, but it's not smearing like a full persistence display. But if you see especially like a dark tree limb in Tuscany and you move your head very rapidly, you'll see one ghost of it offset by a certain amount proportional to your head movement speed. And that's a problem that gets worse as the color palette gets dimmer. The very dark colors have more of a problem with smear. And this is something that we dearly want Samsung to fix in future displays, but it hasn't been their top priority to address, but it matters in VR. We have made mitigation strategies for that, where you can de-ghost, where it's kind of a software overdrive. If you know what color you put in there, you know what color you're going to. If it's higher, you can actually drive it higher than what you want it to be to compensate for that problem. And we've done that on both PC and mobile, but it's really another extra expense that's hard to justify on mobile relative to all of our other problems and things that we want to spend our resources on. But still, in general, darker games are an improvement. But unlike the problem with PCs and console games and the classic Doom 3 problem, where if you make a really dark game, at least in VR, when you can block out almost all the outside light, that can be a much more pragmatic, workable solution than it is for a typical AAA game, where you have to worry about ambient lighting in the living room and so on. So that's one of the takeaways for Gear VR is the super bright pastel-colored worlds, while they play well in VR at a higher refresh rate, they have a drawback that you have to deal with and work around a little bit at the 60 hertz side of things. The big one that is harder to mitigate, though, is the lack of position tracking. I mean, we do all know, we've been talking about presence and how important it is to get that sub-millimeter tracking accuracy, and we don't have it or any analog on mobile right now. And there are things that we've taken early steps on this, where everybody will say, well, can't you use like the AR applications to use the outward-facing camera? And I've done integrations with Qualcomm's Vuforia and tried different things with that. But some of the things that people miss if you pay attention carefully to these slides, one of the things on there is sub-millimeter no jitter, sub-millimeter accuracy with no jitter. And the current things that people can do with outward-facing cameras for absolute positioning are really not close to that. So there's not a great mitigation strategy for this, other than all the things that people would do on DK1 to just try to not have the problem by not having things in the real near field where your body's not interacting with them the way that you want them to. But there's no really killer strategy to avoid that unless you've just got everything in the distance field and no stereoscopy and no near field effects. So that's something that we just kind of have to grit our teeth and live with for now. Now, I have a scheme for both of these. I have things that I think are workable solutions that involve changes to the architecture that we may address these in the future. Because one of the things about kind of hitching our train with Samsung here is that Samsung's technology ticks twice a year. They have big product rollouts 2 times a year, and we expect Gear VR to be kind of following this path. So it's not like it's going to be years between updates here. There's going to be hardware changes and updates, and we can look at rolling out major new features as it goes on. So the paths that I think can address these problems are, for the low persistence display, right now we achieve 75 hertz on DK2. Now, DK2, if you've ever taken one of them apart, it's basically a Note 3 screen. This is a Note 4 screen with Gear VR. So they're very similar, and the question might be asked, well, why can't we just run the Note 4 screen at 75 hertz like DK2? So there's a couple aspects to that. There's 2 things that we do to get the refresh rate on DK2. One of them is pulling out all of the blanking lines at the end of VBlank. It's kind of a weird archaeology of technology thing that even LCD and OLED panels, they still have vertical blanking lines as if they're a CRT waiting for the raster to go back up to the top. And this is just, as display technologies have evolved, they've kept these historical artifacts. So there's a little bit of margin where you can take all of those out, and we would have been able to, and we did have one of the Galaxy 4, one of our earlier prototypes, we could run it at 70 hertz. So the question was, well, is it okay to run at 70 hertz? Is that worth the improvement there? And the problem is, a lot of things that we were looking at are going to be media related, where you want to be able to play back something that was captured with cameras, which is going to be usually a 60 hertz input. In fact, one of the big achievements, I think, over the last year was getting a lot of the work in panoramic photography focused on 60 hertz instead of just 30 hertz capture. But that would have been probably a net negative for a lot of these things if we made a 70 hertz display that would add beat frequencies to anything played back at 60 hertz, and it would make all the normal games another 15% harder to hit that target frame rate, and that was a significant concern for us. And then the last 5%, 5 frames per second that we get out of DK2 is actually by kind of overclocking it beyond what Samsung wants to do to the millions and millions of Note 4s that are going to ship out there. So I don't think that even in the coming years that we're going to see these standard displays that you're just going to be able to turn the clock up to 90 or 120 hertz. And in fact, while we're talking about 90 hertz is the level where most people don't see any flicker. A lot of people can still tell on DK2 that it's flickering, especially if you do the bad things. You put white at the outside edge of the screen, and that's where a lot of people in their peripheral vision will still be able to see it. 90 hertz is where probably 95, 99% of the people really don't see it. We still run across a few people that can perceive it in the valve room or at one of our 90 hertz displays, but that mostly solves it. But I would argue that there's still a strong reason to go beyond that all the way to 120 hertz. And the reason for that is that 120 hertz gives you the even divisions where you can run 60 hertz content with double frames, you can run 24 hertz content at an even thing, or you can run full 120 hertz new frames. But there's very little likelihood that we're going to see these small displays actually running at 120 or even 90 hertz at the size that they're designed for. There's a lot of inertia in the cell phone industry, the small display industry, and they don't currently see a real need for doing that. Although I would argue, and I am making this case to Samsung, that they can probably get more perceptible benefit to the users right now by, instead of revving the resolution even more. Because if you put the 1440 phone next to the 1080 phone, you have to look kind of carefully or interact with it for a long time to tell the difference in quality. And it's at least arguable that if you went to a low persistence 90 hertz display, the scrolling test, which everybody does when they get a new cell phone, how fast and smooth does it scroll? Is the Apple better or the Android system? That they could get more of a perceptible win by doing that. So that's one tack. We are at least saying there are benefits to doing this at the higher refresh rates. But the scheme that I am proposing that I think is doable, that I think there's a real chance that we can get Samsung or some other display manufacturer if they want to step up on this, is the return of interlaced scanning, where interlaced scanning, and programmers are groaning to themselves right now probably about this, but interlaced scanning was invented for a reason back in the 40s and 50s when TV was developed, because we knew that we needed at least 60 frames per second to avoid flicker, but they really could only get the resolution that was acceptable at about half that. So the idea is, instead of scanning all the lines down one time after another, which at 30 frames per second would flicker horribly, you instead go every other line and then every other line on the way back, which means that it's kind of like the low persistence issue, which CRTs are even lower persistence than OLEDs. They have like nanoseconds of actual illumination depending on the phosphor there. But what that does is it gives you the same kind of fooling effect of low persistence lets you imagine the motions that's there, but alternating the lines there, your brain will imagine that it's a solid screen even though you're only updating every other half of it. Now, this is something that I am hand-waving at Samsung, saying, I don't think this is going to be that hard. You probably still have little crufty bits in your OLED controllers that are actually made for doing interlaced displays on NTSCs. I can't believe this is going to be that hard. So if we can get that, then we can run a 60 hertz display with 120 fields per second. So this is not like NTSC, where you can remember the flicker of that. That's a 60 hertz field, and it's not great. But if you double that up and you're running 120 hertz fields, I think that can work. And if I can get that bit, and I think that's a winnable battle. I think that can be done. There's limits to what we can try to influence Samsung on the display side, because obviously they care about the hundreds of millions of cell phone displays, and however much we expect VR to be successful in the next couple years, it's not in that level of units. So we might be able to get them to do minor things for it. But what I've learned from dealing with Samsung, certainly through all the Gear VR side, on the software side, is there's an icebreaker moment where as soon as they push back until something breaks through and they do something and it works out really well based on what I've suggested. And after that, then the doors are open and we can get all sorts of things. Because from what I think will be that icebreaker moment with two-way interlaced displays, there are two steps beyond that I think can provide really significant benefits. The next one would be going to a deeper interlaced display. Instead of going every other line, start going every 8th line, so you have 8 times as many fields, or every 16th for 16 times as many fields. That would give us the kilohertz display that we would really like to see, where it would scan down and you would have kind of like a Venetian blind effect of one image there, and then 1 millisecond, at a kilohertz rate, it would have the next one, and the next one probably going in some kind of an interlaced pattern rather than a straight going across there. So then we could have every IMU update updating the entire visual field of view. We can do something like that now with sliced rendering, sliced time warps, where we can divide the screen up into currently 8 bands, and we can render that band just in front of the raster, and that's how we can get down to this sub-4 millisecond motion to photons latency. But that has the issue of it is motion to photons, but you're only seeing it in a band of your view, and it moves around. And we still have questions about some of the little things, like when your eye does a fast saccade track from one side to the other, if it starts or ends in an area where there's actually nothing in the display, is that causing some subliminal issues for us? And I think that there would be this real benefit to having the entire screen always illuminated with some set of bands that's just kind of moving around as it goes. So that becomes step 2, a little bit more technology there. Probably still doesn't cost them a dime in terms of adding extra hardware to it. It's just going to be changes sort of in the driver chip, in the software that runs that. And I don't know. I don't have access to that level of, I don't have insight into their exact processes, but I'm guessing that that's not that bad. The third step from there, which would start deriving some really interesting benefits for us, would be if instead of saying we've got maybe a programmable mode register that says interlace by 1 through 16 levels there, if instead we make it programmable where the next line that gets scanned to the display is actually determined by the first pixel in the scan line. So at that point I could say, well, I can just in software determine whether it's a linear scan or if it interlaces in different ways, and I could simulate those two modes there. So One more step beyond that would be you add the ability to say which scan lines you turn off at it. Right now, the rolling shutter, low persistence, means it is always scanning in new things and then some amount back that's programmable by Samsung. It turns those lines off. So it's a bright band that moves through the screen. So it's always like scan line, whatever you're on, minus 200 or something is turning off. If we make that programmable then, and we have the ability to say we're scanning in line 50 and we're turning off line 20, then that opens up the possibility of dynamically changing that every frame based on the content that we're putting in there. So we can scan across in like a compute shader. As we do the time warp, we figure out what we're going to put into this scan line, histogram all of the, find at least the minimum and maximum, maybe do some fancier stuff there, but the dynamic range of what's going in that scan line. And then we normalize that to the full 0 to 255 range. So it takes the full available precision that we can put into the bytes that are going out there. And then we determine how long that line will stay visible. So it would be variable persistence based on the dynamic range of the content. This would give us two benefits. It would give us increased precision at the low end, because you could have really far more precision than the human visual system could ascertain there, because we could have a 0 to 255 level that might be turned off one scan line after, which would be 1/2000th of the frame, crazy low values there. So you could have incredibly high precision going there, but then you could also stretch the persistence all the way back up to the full level. Now, full persistence is a blurry, smeary mess like DK1, but if you're normalized to this dark room or the dark head mount display moving around, and then a line comes on full persistence, it's blinding. It's like you do go out into the sun, and you could dynamically tone map all the stuff down, adjust the exposure so that, but you could get that sense of walking out of the dark room into the sunlight, it's all blinding, and then you adapt back down. High dynamic range displays would be a wonderful thing, even for traditional displays. I mean, I've argued for a long time that high dynamic range, it's a chicken and the egg problem for content right now, where we don't have high dynamic range film capture and movie rendering, so there's not much of a call for high dynamic range home theater, but that would actually make more difference for people than a lot of what's gone into either the higher frame rate super resolution or super frame rate stuff, or higher and higher resolution. Higher dynamic range is pretty powerful. Now, this wouldn't be perfect, because if I'm looking at this and I've got these bright lights here, every strip that has a spotlight there would be normalized up to really high persistence, and then everything else would be low persistence. And I'm waving my hands about this, but I think that's doable with no additional cost to the hardware, and it would give us an element of both solving all of the other prior problems, giving us the interlace scans that we can do whatever we want, and giving us some element of higher dynamic range and higher precision on the low end. So that's my plan. I hope Samsung or anybody else listening to this can go and make that hardware happen. I don't think it's that hard, and I think it can make a big difference for us. Now, position tracking is really, I think, a harder problem. I think that the display stuff can be solved just like that. Oh, and the other great thing about that solution, because it is no additional bandwidth, it means that we follow the train to 4K displays without any interruptions. Where right now, every time they get a little bit more analog bandwidth on something to be able to charge the pixels faster or whatever, they want to be able to make it higher resolution, because those are the numbers that people look at. And when we talk about saying, well, we want 90 hertz displays, to some degree, we have to make a choice between resolution, using smaller chunks of screens that scan at a higher rate. But I think that the interlace display may be the possibility that gets us state-of-the-art displays at all times without having to wait for them in some way, while also solving a lot of these other issues and avoiding the bandwidth problems. Now, I think we can prototype this, where we have displays that we can reduce the line count on and overclock a bit. So what I'm trying to get some people internally to find some time to do is take some of our displays, make a 120 hertz display. So basically take something that we can clock all the way up there, whether by cutting lines off of it or actually driving the clocks higher on hand-selected parts. And if we've got that, then I can simulate exactly what an interlace display will look like by sending two 60 hertz fields that actually have black every other row in them. And I think if we can put that together, put it in a head-mounted display, and say, here it is, here's what 60 hertz regular looks like, here's what, say, 90 hertz or even 120 hertz look like real full refresh rate, and then here's what the interlace display looks like. And I'm betting that it's going to be at least as good as the 90 hertz. It's obviously always better to have all the pixels all the time and get 120, but if we can have the 120 solve all the field division problems and the issues with pull-up, pull-down on the judder rates and get it with no additional bandwidth, it would be a huge win. So there's some effort underway that I'm trying to get that work done because, again, I think that'll be really pretty important. For the position tracking, I do think that's the harder problem, and I've got a scheme for this too, but it's even more hand-wavy about it may or may not work. I'm confident that interlace stuff will work out. So for position tracking, the people that have been doing this, like the Valve team and Davin team here at Oculus, it's a significant, challenging undertaking. And again, when you come back to saying it's not just like every little demo you've seen of somebody looking around in something, seeing tracking dots on the world or whatever, but doing it with a sub-millimeter accuracy and without any judder, it's hard. The phones today really are powerful enough that we could run similar calculations. It would reduce battery life and runtime and thermal problems and all that, but it could, in theory, be run there if you had the same external camera. But really, what we all want from this VR system is the thing that you've got on your head that you can look around and you're not tied to anything, whether it's no cameras, no external cables, anything like that. You want it something done with the inside-out tracking. Now, probably everybody's seen demos of the SLAM work where people have an inside-out camera and it looks like it's working going around. But, none of us have yet seen something that really works that well in a completely unstructured environment at the refresh rates and precision and things that we need for this. It may be that somebody's done it, but we keep getting pointed to things that people think will work, and they're just not quite there in terms of everything that we need. So, like with so many things, when you're presented with a really hard problem, and the way to address it often is to figure out how to make it not such a hard problem, basically how to cheat. And that's not always looked at as and we have some of this at Oculus where the fact that we know how to do it really right, we have the pure way of doing it. Arguing sometimes for something that's not quite as pure is sometimes a little bit of a battle where should we just wait until we can do the purely right thing? But I think that there is a middle ground on this that can provide many of the benefits where the hard problem to be solved right now is a 6 degree of freedom problem. It's finding where you are relative to a specific point, and this is sub-millimeter precision. It's really hard. And you wind up using that, you coast on your IMU integration and everything in between that, but you have this continuous absolute sense of where you are relative to the camera and then relative to the world around you. And that's a wonderful thing, but what we need out of the position tracking is really not so much this absolute reference to the world. What we need it to do is be close enough to what you're seeing from the headset's point of view, not so much relative to the rest of the world. Now, what we've been doing with sensor fusion and the basic IMU stuff since DK1 is taking relative sensors. The rate gyros, they don't tell you which way you're pointing. They tell you how fast you're turning. And we integrate these and we do all the sensor fusion stuff to basically say, well, they're not telling us where we're pointed, which is what we really want, but we keep track of it, of all the turns that we think that we've made, and we fuse it with some other sensor data, and we wind up with this estimate of where we're pointing. And we use the accelerometers to correct tilt up to this for gravity. We use a magnetometer to correct yaw relative to this. But they're still approximations, and you're not within a couple degrees of dead solid accurate with this, but it still works pretty well. And I think it's possible to do a similar thing with the position tracking where if we don't care about absolute knowledge, saying that I am 57.2 millimeters from the camera, and I've translated 2.7 millimeters since the previous update. If we give up on that and say all that we really need to know is relative velocity, basically camera space relative velocity, that's turning a 6 degree of freedom problem into a 3 degree of freedom problem, and it winds up being something that is potentially a whole lot smoother. So this is where I have a little bit of effort on going to this, where I think that I can make this relative motion sensor and make that work conceivably on the mobile systems within our sort of power and graphics budgets and the things that we need to do there. But that's a lot of hand-waving. I'm hoping to to be able to have some kind of an existence proof on that within the next couple months, as soon as I can pull away from the crunch of shipping on the, actually shipping the first generation product and start working on what goes into the kind of the generations after that. No guarantees that's going to work out. There are fallback plans there are other sensor technologies that can be used. We have, Qualcomm's hard at work trying to make their technologies work better for this. Early on, I did use Qualcomm's Vuforia augmented reality platform to do a basic set of motion tracking on mobile, and that's something that lots of people will probably be trying to do this, because you can go get it. It's kind of fun to integrate. It's not close to working well enough, both because of the accuracy, there's jitter involved in there, and the basic way that works. The standard Android camera interface gives you this 30 hertz camera, which is lots of smear and blur. That was never going to work out well. But we do have, one of the things that Samsung's done for us is given us a path to get 120 hertz camera updates, which does wonders for anything that you're trying to do vision-wise. 30 hertz is almost impossible with the amount of smear that it has. But at 120 hertz, you're looking at pretty good images that are pretty reasonable for analysis. So if Qualcomm or somebody else comes up with some magic that lets us work with that, there might be intermediate things, like if you could have one marker in front of you, it could even be like a little unfoldable placemat or something. That might provide an absolute frame of reference, and if you move around and come back to it, it might work out okay. So those are the two Achilles heels of mobile right now. The low persistence video at 60 hertz can cause flicker, and the lack of position tracking can cause discomfort, depending on how you move around. But that brings us to the things that are actually really awesome about the mobile experience. And some of these are things that you really don't appreciate until you've really experienced them. You might not be thinking about them and why it makes it so great. But like Brendan mentioned, the ability to have the headset and just hand it around to people, to just say, here, try this, rather than bringing someone into your VR lair and hooking them up with all the wires and everything. It's a different experience. You just can carry it around with you and show it to people. And it's that has a power to it that you don't see, that the kind of casualness of it, and the treating VR like you treat a tablet rather than like you treat this experience that you're setting out to go undertake. So there's an important aspect to things like that. One of the obvious ones is the fact that with no wires on you, you can turn completely around 360 degrees and you can keep turning. And this sounds like a really trivial thing, but being able to play a game, again, like Brendan says, we never talk about standing, but if you can play a game on your, like on a swivel chair, you can sit there. And no, I mean, you laugh, but this is a bigger deal than it probably sounds like at the beginning, because one of the core comfort problems we've got with navigation, and even with all the stuff Brendan talked about, all the magic that we've got now, and everything we even know how to do in the future, it doesn't solve the yaw navigation problem, where if you're sitting there and you stick yaw and the whole world spins around you, it doesn't matter if we nail everything else. That is still sickness-inducing. It is still one of the hardest things, and few people can sit and play Half-Life 2 for a couple hours, playing the game like that, because it is hard. And yes, we'll find some people that can steel their stomachs and push themselves through it there, but that is clearly not the comfortable experience that we've been talking about that we want people to get in VR. But if you want to explore the world, if you can do the turning in the real world, whether by literally doing this or spinning around in your chair, and all you do is go forward and backwards. Yes, every change in velocity is a little lurch. It's a little punch in the gut, but the continuous yawing, that's the really bad news part of it. So if you turn and all you do is go forward and backwards, and as should be drilled into every developer now from all of our best practices, you don't want to ramp up the speed. You want to jump to the speed, be at that speed, and then jump out of that speed. With that, you can explore the virtual worlds the way people always want to. And even we've been building all these things with seated experiences, or the things where you really don't navigate around and you have neat stuff around you, and that's all great. There's a lot of things that we can do, but after the 50th turret shooter game, I think that the genre is going to get kind of tapped out, and we're going to be wanting to do different things. And even in our things like the theater, it's the magic of VR is seeing this place, believing it, then wanting to explore it. in our theater models, you see when the lights come up and you see down there, I want to go down and see what's around the corner there. I want to explore the virtual world. I don't want it to just be this shell around me. So I am very excited about the possibility of people building games that involve navigation that take advantage of saying that, well, okay, we'll still have a stick yaw, so if you're sitting in your easy chair recliner and you can't rotate around, then you'll have to do it like this and it's going to be uncomfortable. But if you can sit in a swivel chair and move around, you can probably play for an extended period of time, explore the world, and do the things that people have always really been wanting to in VR. So I think it sounds like a trivial thing, but I think that like swivel chair VR is going to be a kind of a big deal for writing a lot of those experiences that people want to see. So the Gear VR, as it turned out right now, is pretty good. I hope everybody gets a chance to take a look at what we're showing at the demo. Some of the things that I want to point out in particular, so the resolution of the panel is the big thing to sort of crow about on Gear VR, where it is a 2560 by 1440 display on the Note 4. So this is significantly higher resolution than DK2. So it's everybody that complains about resolution, it's still not solved. Like Michael said, we are at this very, very low end of the resolution. We need orders of magnitude more to really get to this Retina class display. But doubling the resolution is a damn good thing. It helps a whole lot. Most of the stuff in mobile we render at still a fairly conservative kind of eye texture target size. The default, if nobody changes it, is only 1K by 1K. So we render 1 megapixel per eye, which is less than the number of pixels on the display. So they get stretched up and distorted onto it. But that's usually the right trade-off. You can render more, but mobile runs out of juice on the GPU or runs out of power earlier. And it's a good trade-off. And in fact, one of the tragic mistakes that happens to a lot of Rift demos and games is through miscalibration of the eye relief and using what the SDK returns to you. A lot of demos when we see that have tragic performance are because they're rendering at some ridiculous resolution, like 1800 or 2K on some eye, because if your eye is jammed that close, that's what the center pixel, the next pixel step would ask for, and that's never the right thing for anybody. I've argued that we should have conservative defaults on the PC as well, just to prevent that all too common mistake from happening. So the 1440 display doesn't actually help all that much if you don't change the size of the eye buffer. And we had, when we migrated from the 1080p to the 1440 display there, the thing people commented about was better pixel fill. Even if there were no new pixels sent to it, it looked better just because the pixels were smaller and they filled out the area a little bit more. But we do have some applications that take full advantage of the display resolution. And the way this happens is, instead of rendering to the eye buffer, then distorting that eye buffer onto the screen, there are a certain class of things that I call overlay effects in the mobile SDK, where we can have the normal display that's rendered at, say, 1K that's stretched around, and then we can sample some analytically specified things. And currently it's either a quad in the world and anywhere in full perspective or a cube map surrounding it. And we can sample those textures directly, which make them completely independent of the resolution used for the normal eye buffer. So this means that the movie theater screens are rendered at the full resolution of the screen, which is still not what you'd want, because it's a 2560 cut in half, each side is 1280 by 1440, and you don't usually watch a movie theater at the full 90-degree field of view. It's pulled in. So you wind up with, your movie screen resolution there might still only be 960 by something, which doesn't sound good relative to, high-end stuff, but it's still a lot better than what you've seen in VR so far. But kind of the more exciting for me application was the panoramic stills. I think we call it pano photos or whatever it is in the current setup. But we have 200 photos that we licensed from 360 cities. And one of the real eye-opening things for me this last year was seeing how much really amazingly beautiful panoramic photography there is out there. Now, everybody's looked at a pano photo on their computer or tablet, and it's just not a good experience. I mean, you can swipe around and zoom in, and it's a gimmick that's a little bit interesting to look at, but it doesn't really deliver anything. Looking at them in the VR space it's a completely different thing. I think it's going to totally legitimize that entire field of photography in a way that it hasn't been before. But so for these particular images, we curated out 200 images. I resampled them to exactly the right resolution for this, and then they are displayed with this time warp overlay shader, which means that these are drawn at just about the best possible display presentation that you could get from this. So the resolution that I wound up using was 1536 by 1536 cube maps, and that winds up being me rounding to a power of 2 or multiple of a power of 2 for probably no good reason right now. And you can think 1500 or 1600 cube maps as the side there. And that's based on making about the middle 40% or so of the view not have any MIP mapping, and then fading to the MIP map as it goes out for the distortion there. So in the center of the screen, you've got very close to a one-to-one mapping from that image to what you're displaying. And they look really good. There's a lot of times when we've seen people that get into some of that and are just looking through all the photos, and it is such a dramatically different experience than looking at those same photos on your computer. But it's the best demonstration of the resolution of this device that we've got. So I hope everybody can take a little look at that and just see what this is, kind of the peak display quality. The other thing I'm doing on there is it's all gamma correct on the refiltering, so it's sRGB setup, which still costs you a little bit on mobile, and usually isn't worth that much. You kind of have to search for the best cases that show off why there's any value there. But in showing the static photos there, it does have a little bit of extra value. And I wanted to just kind of nail this just about as perfectly as possible as the example of, here's what we can deliver on the display. So what you want to then imagine from that is saying, look at the panoramic videos or the stereoscopic panoramic videos and say, well, these are at much lower resolutions for a number of reasons I'll get into. And where we want to be is to have that full quality of the static images, but have that then be stereoscopic motion from there. And one of the things that really made me think that I had crossed an important threshold is we have Seneca, one of our fantastic artists that work on all these things. He's usually down on all this stuff. He's not one of the magic of VR people there, and he'll be complaining about the blur and the quality and the filtering. And he had looked at a bunch of the panoramas and just like, nah, kind of blurry, not that good looking. And finally, when he said that the final version of this overlay shader stuff with the pre-sampled stuff, it's like, yeah, that looks pretty good. I think there's a threshold that had been crossed where it's considered acceptable even to somebody that's really picky and is probably going to be, past any necessary threshold for kind of the general public there. So the other things that we'll see on the other things you need to check out on Gear VR is the panoramic stereoscopic videos. And this was one of those things that there were significant debate over whether such things should even be condoned internally, let alone promoted. And the reasons for this are stereoscopic panoramas, whether still or videos, are absolutely a hack. We know what right is and this isn't right. What they wind up doing is you've got slices taken from multiple cameras, so straight ahead, it's the proper stereo for a pair of eyes, and then, over here, it's proper for this. But that means that if you're looking at what was right for the eyes over here, but you're looking at it out of the corner of your eye over here, it's definitely not right. It's not the right disparity for the eyes. And then even worse, if you turn your head like this, it gets all kind of bad because it's set up just for the eyes straight ahead. So this was an interesting thing. We've got this stuff where we basically know, in some ways, this can be poison. This can be a really bad experience if people, spend a lot of time slouched over like this. But the argument is that people do watch 3D movies in theaters that have the same problem. If you turn your head sideways in a 3D movie, you're seeing the wrong things. It's worse in VR when that consumes your entire field of view. But there's still the argument that people do accept these partial steps. And this is a struggle inside Oculus because, again, we know what right is. We know how to do right, and we're working on doing right. Is there value in taking intermediate steps and accepting something that we know isn't right? And the final conclusion was that, yes, this is one of the things that people reacted very powerfully to. And we started off with some early panoramic videos that we had gotten from different places. And one of my big successes this last year was, again, getting more people to do 60 frames per second panoramic captures rather than 30. Because a lot of stuff was based on GoPro rigs, and you've got, there's all V-Sync issues and different camera capture stuff. It's the Wild West right now in capture for panoramas, and I think that's going to be exciting to see what happens over the next year because this is going to be a pretty big thing. But one once you get to the 60 frames per second, you can have like the moving tours through things. You can have the helicopter rides, and they look really good. The motion is great, low persistence, and everything's good there. But a normal panorama, like a normal panoramic photo, everything's at infinity. There's no sense of near-field objects. And there's a lot of wonderful, artistic, good-looking things like that, but it's not that sense of, of presence directly. The stereoscopic panoramic videos, under the right conditions, under the conditions of you still have no sense of translation, you'd better not turn your head sideways, it's best if you're focusing on straight ahead, but they can deliver that sense of something's right there. And I was extremely impressed by the Felix and Paul videos that they've done, the Patrick Watson Stranger, and so Oculus and Samsung contracted them to do the out-of-box experience video for Gear VR. And it has scenes that were shot in a few places, and they worked with another company to do some CG scenes set up for this stereo panoramic video. And it turns out to be really pretty impressive, and that was what we want everybody to experience the first time they put it on their head. It's got scenes that are coming from the real world, coming from synthetic things, and they have that sense that you really are kind of there, the real world is still more complicated than anything we synthesize, even on the most high-end systems in real time. So there are going to be large sets of things that, even on these crazy high-end PC systems, we still cannot convincingly simulate. This room, with all these hundreds of people here, this is not something that we can make a plausible, real-world quality simulation on, even on the highest-end GPU. So there are all these things that people would like to be recording. And one of the things that really was one of my high points of this project here was seeing Felix and Paul had Cirque du Soleil take some of their props for one of their shows, and they built a little VR-specific skit for this. And they had performers coming onto your side, something going on in front of you, and they're talking to you with positional audio. So you wind up looking over to them. And this is something that's showing the barest beginnings of the hints of the artistry that's going to be brought to bear. So I do think that this type of thing, that the panoramic videos, is going to be a big part of the Gear VR and eventually VR in general, because I think it can do a lot of things that we still can't simulate. So if we go back to, so this all started a little over a year ago, when I first came to decided that I was going to go full-time at Oculus, or when I was first coming down to talk about this, we knew everything that was going on we had HD, DK at that time. We really didn't, DK2 was not really even a gleam in terms of what it was going to be, because we didn't have the deal with Samsung going yet, all these different things for the displays. But one of the things that most excited me at that first meeting was learning that, so Brendan was going to Samsung all the time we want OLED displays. Everybody knew we wanted OLED displays because initially, just because super fast pixel switching, no blurry switch, and then as everybody grew to understand the importance of low persistence from Valve's work, that became the display technology we wanted. And the way Brendan told the story to me when I was first getting there was, he's going there trying to kind of get the buy-in on selling screens to Oculus, and he's not exactly getting everywhere that he wants to go with Samsung there. But then one of the Samsung people sort of pulled him aside and said, well, we'd also like to talk to you about this. And they pulled out the first of that little 3D printed phone holder that was something that they had been working on, and they had decided that they wanted to work with Oculus on it. So I got to see that first little demo that Samsung had put together, and it was what you'd expect. It's a phone holder like Cardboard or like VR2Go before that, or like a bunch of these other projects that's been done. And it was a quick spark for me, because I remember a couple years previously when I was first starting all this VR stuff, one of the things that I got was the little Hasbro drop-in iPhone holder. It's like the little Viewmaster looking thing, stick your thumbs up there. And of course it was terrible, but when I looked at that, I saw it doesn't have to be terrible. There are all these straightforward things, and I almost drafted up a big email to Hasbro at the time about these are the things that you need to do to fix this experience. It could be really cool. And I was doing that at that time with all sorts of companies, but so when I saw the Samsung project there, I looked at that, and of course their first demo was well, their first demo showed why they came to Oculus about it. It was just not a, it was not a compelling experience in any way, but it had all those problems that I had seen in these aspects before it. But it doesn't have to be like that, because what we're looking at, all the rifts are really, it's a display that could be driven whether it's by a PC or by an Android GPU, and the sensors are similar between what we've got in the phones there. It should be much better. And I looked at that and said, this is a challenge that I know what to do on this, and I think it can be really important. And that was really one of the large motivators for me wanting to go all in with Oculus, where I mean, all the stuff at the high level is interesting, but a lot of the action happens at the lower end of things. I mean, historically, through all sorts of technologies there, it isn't the bespoke, super high-end thing that winds up changing the world. It's the thing that everybody carries around with them and that everybody winds up having. And I'm dead serious about wanting to see 1 billion people with VR, and I think a lot of that's going to come from sort of raiding the low-cost parts bins there, from cell phone-type technology, where it's great to have a range. You want to be able to have. It saddens me that there's not a greater range in computing now. People talk about how the greatest phone that you can buy is one that probably most people have here, irrespective of money. You can't spend 10 times as much and get a significantly better device. It's great that we've got high-end triple GeForce crazy platforms that we can run these incredible high-end experiences on. I wish there was even more that you could get. You can't go out and buy Silicon Graphics Infinite Realities and spend $250,000 like you could in the 90s back in the old days. The best stuff you can buy is gaming rigs, and that's great. But at the low end, it's still possible to do a lot of these things, because to say the mobile phones are really quite powerful now. The Note 4 is at least arguably the most powerful cell phone. I'm sure I could write a benchmark that could win relative to something else, but they're all incredibly powerful, and they're much more powerful than video game systems from not that long ago. I mean, yes, you'll keep hearing the marketing hype about when they're as good as the current generation or previous generation of consoles, and that's usually overblown for some specific technical reasons that I'll get into a bit later. But in any case, they can run some pretty good experiences, and it is an insult to the games of 15 years ago to say that you can't do anything great unless you've got all the power of a modern PC. It's just not true. But so I was excited about this project. We undertook to go work on this, but there was at the beginning this sense that, okay, yeah, we are hedging our bets a little bit on this experience. We can't do really great games. Maybe it needs to be a more media-focused experience there, that we need to target these things. And the other logic behind that was, anytime you're launching a new platform, you need to think about what are people going to be able to do after they play your out-of-box demo and whatever you include with it. What do they do on day 2 and day 3? You need to have some way to have enough bulk in the catalog there. So there was a lot of focus early on about movie viewing and looking at other ways that we can take advantage of existing data sets. We had a music visualizer, but we've got a couple other partners now that are working on music visualizers, so we kind of dropped that work. We have a great arcade emulator that we struggled through a whole bunch of licensing stuff, but I think it's all worked out now, so work's ongoing about that. But ways to use existing things while the VR ecosystem can develop sort of the from-scratch games. So there was, from the beginning, this little sense that it was going to be a little more media-focused than what we've done on the PC. But that drove us into a lot of research on the video playbacks and different things like that. But the core thing, once we took this not very great experience, and anybody, you can go get essentially the same experience where, really Google Cardboard is better than what the first cut of the stuff from Samsung was like. And by the way, I think Google Cardboard is a wonderful thing. I think that it's been great for Oculus and for VR for Google to have done that, where I think it was a very wise choice to position this and actually make it out of cardboard so people will not judge it too harshly. And we fret about this all the time at Oculus, about when can we stop calling things developer kits or innovator editions because people will judge us as a consumer product. And it's a common topic there. And I thought cardboard was really kind of a brilliant way to sidestep all of that and not have people judge Google too harshly for what it was. But I think it's a great thing, and it shows what you can do just dropping the cell phone in there. But that's using the cell phone sensors, and it's going through the standard Android systems. So identifying the key reasons, why is that not as good as what you see on DK2, or even DK1 for that matter? And that was what I really spent the last year, identifying what those problems are, and then figuring out how to get them It was me alone in my carriage house doing all of this, this work in my home office there. And then finally, 6 months later, we pulled more people onto the project and we started kind of professionalizing the effort. But the first thing, before I got there, Oculus had done They made a little printed housing, and they glued on a DK1 sensor there, and went through and got the, that going through the USB subsystems, and that it turned the calibration, because essentially internally some cell phones use the exact same sensor. They're just really not calibrated. Can find the same sensor inside some phones. I don't know exactly whether Samsung had those ones, but generally in Android you're limited to 100 hertz updates, which adds a jitter of up to 10 milliseconds before you get it from if you have an impulse right at the beginning of that. And the better calibration keeps it from drifting off too much. But that still wasn't really the killer. That was the biggest thing once I started looking at the problem and poking at Android a little bit, and this was all brand new to me, where I had taken a brief look at Android maybe 3 or 4 years ago when I was doing iOS development, and looked at that and it's like, oh, that's going to be a mess, all the fragmentation, and I backed away from it. So this was my first real working with Android, and I've got a lot of negative things to say about some of the Android development experience, but some of them are fundamental. They're having a market that is as large and fragmented as what they are, and having to support all that makes it hard. The reason this project was kind of nice because we had a tight relationship with Samsung. It might as well be a console in terms of targeting one specific device there. So that's a really good thing. But after writing my first rotating triangle in Android and starting to make timings about that, it became clear that the biggest problem on the latency was that Android by default triple buffers all the graphics. So you render something, if you're pushing all the frames out, milliseconds behind if you're rendering something really simple. So that was a huge problem. We've got this 20 millisecond bogey that we want to be under. We want to be under 20 milliseconds, motions to photons, and here you are saying, well, it can take up to 48 milliseconds before your pixel even gets to the display scan out for getting the things before and after. So Samsung's suggestion on there is like, well, we can probably hack things to turn that into double buffering, and that can save one frame off, but that's still not good enough. So what I was pushing for is saying, what I want is, give me the front buffer. Don't swap at all. Just say, this is the buffer that's being scanned out. One of the reasons that this hardware composer layer, where it's kind of like allows you to have an image that might be changing in memory overlaid with other things so it doesn't completely break the experience and make all of Android unusable there. So I was arguing, I want this front buffer support. I will time it myself. All of these displays, the cell phone display VR are portrait modes, and we turn them sideways. Now, unfortunately, Gear VR scans left to right and DK2 scans right to left, which I'm sure is going to cause some low that people from back in the 80s, if you were ahead of it, you change your color palettes or whatever. But this is a mode of game programming, or why the problem exists. This is why this solution will solve this problem. This is why your proposed solution will not solve it as well. Can we please do this? And it was, it was a brick wall for like over and over. And when we finally got Max on board, he heard me just going on about this. It's like, why can't we get this about how some of these things work? And I tried a few really, really ugly things. It allowed me to demonstrate. Then I had a device where I could say, here, look at when it's trying to convince you to do something you really don't want to do for whatever. the ice was broken, and Samsung made a nice interface for it that worked across all the other phones. And after that, Samsung got me crazy things. I mean, things I would never have thought that I would have gotten out of Samsung before that. So there's an interesting aspect of this, though, is that hack that I didn't work on any of the other phones. It only worked on that phone. So I've got this little creeping fear that, like, what would have happened if I hadn't been using that phone, if I had never been able to make that ugly hack that would have convinced them. I think Gear VR would have been a very different product right now, because all of these cool things that I got happening might not have happened at all. So I think I've got that same situation now with Samsung hardware, where they're completely separate divisions here. So the software side, they now believe in by judgment on these things, and they will go and do useful things. The hardware team doesn't yet, so I'm hoping that I've got that icebreaker is going to be that interlace display, that if I can get them, give me two-way interlace, and it's going to win big. And the other argument that I make for them is like, okay, still, all these people, you don't care anything about VR. What the other thing you can do with that is all of your cameras are capturing now at 120 or 240 frames per second, and right now you just use that for slow motion. But if you make interlace low persistence display, you can play back 120 hertz for like hyper real playback that you can't get on any other platform. So that's one of my other wedges that I'm trying to get in there. It's like, and I think it's going to be the same thing. I get the one breakthrough, and then I can convince them to do the other crazy stuff with variable persistence and dynamic scanning and all that. So that's my experience kind of with working with Samsung through this stuff, where there was the feeling out period where there's a lot of skepticism and reticence to change some of these things, because they're going to have to maintain this across all their phones, regardless of whether they're VR based, and there's reasons why they don't want to go do crazy different things in there. But once the ice is broken and everybody believed in the product, and both inside Oculus and inside Samsung, there was this period where there were skeptics that didn't think this was ever going to work out well, people that really weren't behind the project. But as it all came together and it became clear that, yeah, it actually is going to work out and it actually is going to be good, then it's a positive cycle there, where you wind up saying, well, more people get buy-in, you get more stuff done, and it makes it even better. So again, in the end, I think it turned out, and it was really a pretty good thing. So the next major challenge, the thing that happened in the big education process with Android, was the CPU clocks and power management, so I started off, I got the front buffer stuff, I've got low latency here, and now I'm trying to make some applications for this. So I start off working with basically Tuscany, the Oculus World demo, and I'm going through making it faster, doing all the normal, the stuff I've been doing for decades. Here's how you just make graphics faster. You set up the batches, operate more efficiently, doing all this. And I was making some panoramic video players and all the different stuff. But what I was seeing when I'm syncing this stuff to the front buffer myself is it would still be kind of glitchy. It would still have these regular glitches, and it just wouldn't be as stable as I wanted. And it was so frustrating, because I'd go and optimize the hell out of something. I'd make it a lot faster. I'd cut out triangles. I'd cull things, make the CPU and GPU, and everything should get faster. And then it still winds up hitching occasionally. And I'd be looking at some of these videos that were playing back in 57 frames per second. What's the problem with this? And then I found by accident one time that if I was resting my finger on the display screen, it played back perfectly smoothly. Like, what the hell? And there was even a point there where we had a little discussion about how we could make a good demo. Palmer mentioned that if you put a little lithium-ion battery cell on a capacitive touch screen, it registers as a touch. So it was like, well, maybe we'll make one of our little drop-in headsets with a little battery right there to always get onto this. But finally, I got someone at Google to educate me a little bit about what's going on here. And this is all of the dynamic frequency and power management stuff that goes on with Android. So power is a big, big deal in mobile. It determines your battery life, and that's one of the big things that people make phone buying decisions based on. So they go to great lengths to try to minimize the amount of power that they burn. And one of the tools that they have, the biggest tool in saving power is always do less work, write more code. But you can't, there's millions and millions and millions of lines of code, and a lot of it's Java going through all the Android systems. So it's hard to just say optimize all of this stuff. But one of the things that they can do is they monitor how much CPU you're using, and they also do this on the GPU. And if it looks like you're not using most of the GPU, they can turn the clock down. So one of the aspects of the way all of these systems on chips work is that they've got a maximum clock rate, and the lower you can clock them for the same amount of work, the more power efficient it will be. If you've got something which takes 1 billion operations a second, and you clock it at 1 gigahertz, it will use about 25% less power than if it was clocked at 2 gigahertz and it slept half the time. I mean, in an ideal world, you have your maximum clock rate, you sleep when you're not busy, and it all works out. But the reality is that you can save power. Going fast costs power. That's why we've got the big fans and heat sinks on the high-end PC rigs. So what was happening is that I'm timing everything now for drawing to the front buffer, which means I work out what the vsync timing is, and I sleep until a particular point right before wherever it is on the screen that I want to draw. So I would be doing some work, and then I would sleep for a while. So it's watching activity. It's watching and saying, well, you're sleeping X% of the time. That means I can turn the clock down a little bit. But what that means is, as soon as you miss a little bit, so I'm going 60 frames per second, they're turning the clock down, something hiccups, and I drop over, and now I drop to 30 frames per second, which meant that I'm sleeping a whole lot more. So then it says, oh, you're using even less of the CPU, so I can turn the clock down even more. So it winds up being just too slow processing, and that was a big problem, because it's something like, how do you optimize for this when the better you optimize, the more they hamstring you for it? So one of the other really big deal concessions from Samsung was the ability to let us lock clock rates on Gear VR. Now, this is something there were subtleties to this, where the first cut that we had on it was basically setting a minimum clock rate. So it would you could say, well, I want a minimum of 1.2 gigahertz, but they would still dynamically watch this and ramp up. Now, when we got that out to some developers, and we'd say, okay, you want to try to make yourself work within the lower clock rates, it was hard to tell whether you were working there, because if you were a Unity app that's using pretty much all of 2 cores to run all of this stuff, and you say, well, I'm going to try running at 1 gigahertz. You set it there, it starts out at 1 gigahertz, it hitches for a little bit, and then it's brought the clocks all the way back up to 2 gigahertz or something there, and you're burning all that power. What we finally did settle on in the latest builds, and most even the developers that have been working on this don't have the latest builds and everything going into it, is a real locked clock rate, where you set this and it's just like having an old computer at a fixed specific clock rate. But the other aspect of this that was not obvious at the time was the importance of thermal management, where on PCs, again, you've got fans and heat sinks, and you can burn hundreds of watts doing all of this. On mobile, you're burning just a couple watts, but a lot of that energy winds up being waste heat that stays in the handset. Now, there are a couple aspects to this. If you get things hot enough, you've probably felt a phone that's kind of warm to the touch. There are all the policy things about how hot is too hot. You're not actually going to burn yourself, but they can be pretty warm, and there are internal battles in Samsung about exactly what is acceptable there. And the health and safety people will say some small number. The VR people will say we need some much higher number, because if you pick that small number, you're just going to clock down almost immediately. Because what happens is when you use one of these processors and you actually load it, you draw a lot of graphics, you use a lot of CPU, it's soaking up these watts and it's heating up relatively quickly, and it'll eventually hit a thermal limiter where it will start saying clocking, reducing the clocks. So if you've built your game, you've optimized it for a specific clock rate, and it starts clocking it down, well, you can expect the VR experience is going to get terrible, more so than in a traditional game where dropping a frame is not that big of a deal. In VR, it means we wind up with judder, and we have problems with all this, and it's a real big deal. So what we have now is the ability to choose a balance. You get to pick your balance between CPU and GPU power. And so this is actually pretty nice, where you have a matrix of 4x4 values where you can say, I need a lot of CPU, but not necessarily much GPU. And there's about a factor of 2 difference between this. It runs something from a little under 1 gigahertz to 1.8 gigahertz on the CPU, and I think we go from 240 to 600 on the GPU. And you're not even allowed to choose max in both. Now, the device can run that way, it just won't run that way for long. I think that if you look at the specs on these devices, it's like 2.5 gigahertz 4-core processors with a 600 megahertz GPU. Clock for clock, they're not as good as an Intel processor, and some of the other ARM ones are significantly worse than that. But still, it's pretty powerful. But if you spin up a 4-thread program with the GPU running there, and you turn on the camera and Wi-Fi, and decode a video in the background, you'll overheat in like 20 seconds or something. It will just, it'll suck all that power in, it overheats, and it shuts things down. So it's a real issue, and this is something that we're still not exactly sure what our messaging is going to be on this, where some applications, cinema obviously has to be able to run steady state for 2 hours. You need to be able to watch a full-length movie in it, which means that it uses hardly any CPU. It's on the minimum CPU setting because it's not calculating anything. It's decoding a video that's going up there. But it does come into, it's got some reasonably heavyweight graphics going on. It's using the overlay plane technology to get the super resolution on the video. It's doing dynamic lighting on all the world around it, and that becomes a little dicey. We find okay, we can just barely fit within the 380 megahertz level there. But we do wind up now having a floating screen option where you just can have the screen floating in black, which saves a ton of power, but also allows you to do things like watch a video on the ceiling or something, or lay down sideways in something that, it's worth noting that some people said, well, can't we just rotate the theater or something there? And that was one of those clear misunderstanding about the whole VR experience, where if you have your up vector in the virtual world and it's not also your physical up vector, that's breaking what we want to try to accomplish in VR. And so this balance is going to be an important thing for developers to be finding, and in some cases it may mean making concessions on your graphics, but there's probably going to be a space for games that are really pushing it that will, after 10 minutes or something, say, we don't know the messaging on this exactly yet. Samsung really doesn't want us to say like thermal throttle or thermal overload. I want a little cell phone on fire icon or something. But we're not sure exactly how we're going to message this, but one of the things that we can do with it is give you the option of continuing or playing in a degraded fashion or exiting VR and going on to something else. So something that we have the option of doing here on mobile that we don't on PC yet, and I'm pushing hard on this because this is probably the most important result coming out of the mobile environment, was this the asynchronous time warp notion, where it was one of the very first things that I tried when I started on this project. The idea is that if we can decouple the refreshing of the screen, which we know has to be 60 or 90 or 120 or one of these very high numbers, from the rendering of the eye buffers that go into that would be a huge benefit to developers. It would allow you to, in theory, have a 30 hertz game that gets updated to the screen 60 times a second. So we know that the basic time warp principle of you can take an image, you can warp it to another place in space, and for attitude-only adjustment, that works wonderfully, although there were lots of arguments internally where, again, you win arguments by showing an existence proof. I mean, there were a lot of arguments internally at Oculus about what the downsides of this was going to be, but just went ahead and did it all in mobile, and we can look at this and say, yes, this turns out to be a good thing, and so we have interpolated time warp on the PC now, but the important point here is working towards asynchronous time warp. So I tried it first on mobile, the obvious way. You spin up a second thread, you pass off buffers between them, and it didn't work for the equally obvious reasons and expected reason that GPUs are all about throughput right now. They really are not optimized for latency. They are optimized for soaking up this immense amount of work and then processing it at some point in the future. So the batching that happens here is not very well controlled. To have this asynchronous stuff work, I've got this window of half of a screen while it's going on the front buffer, 8 milliseconds. So I need to know that I can draw that half of the screen within 8 milliseconds of the time that I start. And there's a bunch of things that go into eating up that cushion. There's the scheduling on the CPU, where if the CPU wakes up 10 milliseconds later, it doesn't matter if your GPU is infinitely fast. But it also means that when I put in that little bit of drawing, draw these 1,000 triangles or this slice of it or whatever, that needs to happen before that window runs out. And the way most GPUs work now, they love to have 20 or 30 milliseconds of work buffered up. That's the way they get their best benchmark scores and the way things look really good if you want to render out to 4K displays or whatever. You want to bandwidth optimize for those situations. But in VR, we have these very, very tight latency optimization requirements. So what needed to happen was that you needed to be able to prioritize the work in some way and say, this is much more important than this. And GPU, when this comes along, you need to stop doing this and do this instead and come back to it. Now, the very first phone that I had working on here was, again, the Imagination Technologies phone, and they actually have an extension for this. It's like IMG Context Priority. I'm thinking, well, this is exactly what I want. The minor fault there was that you couldn't, in their particular implementation, you couldn't have multiple contexts in the same process with different priorities. So I would have had to do something really gross about spinning up another Android process and somehow passing the images as external images between the processes. And it would have been basically like Android's compositor surface flinger. And I did not have nearly enough confidence in my Android skills at the time to want to spin that up. But as we were going through this whole development process, by this time we had some good-looking stuff. We had the locked clocks. We had Sched FIFO real-time scheduling, which was another huge concession from Samsung to get in there. We had our kernel driver for the Oculus sensor rather than winding its way through the standard USB input stack. And these were giving us this low. We were well under 20 milliseconds of motion to photons latency, and it was looking great there. But the problem was everybody was looking at this and saying, okay, John, your 3 applications run 60 frames per second reliably like this. What about all the rest of our developers? What about 90% of the developers were Unity developers, and where Unity is just not working that well under these conditions because rendering to the front buffer there, low persistence, any little glitch on garbage collection, anything that just happens to load slightly incorrectly. And in a multi-million line code base like that, there's just a lot that can go wrong. And unfortunately, like the way the SDK rollout on this stuff had gone with developers, when I reached a point where I had kind of the few native applications that me and a couple of the other guys had been working on, and we were making those available as source code, we made the first, I don't even want to call it an SDK release, but the first batch of developers that got some code from me got sort of our sample code for these things. They could do a few things, but the Unity integration wasn't ready yet. And we really kind of mismanaged that first rollout of the 2 developers where it was still a matter of the whole company hadn't really kind of gotten on board with all of this. So we wound up with a dozen or so of our most hardcore kind of Oculus Connect sorts of people doing the development for it that were largely the Unity-based indies. And so that first rev kind of went out, and nobody was like, well, we're not doing native code. This kind of just sat there for a while until I got the Unity integration working well enough. And again, the latency worked out fine there. It was the variability that was the problem. We could make some Unity-based experiences that could be almost consistently 60 frames per second, but it was hard to really make them absolutely reliable. And there was, again, real doubt about, well, this may not be a viable platform for gaming. We can do our videos, we can do our hand-coded native things, but it's probably not a Unity gaming platform. So the thing that allowed that to actually come to fruition and become a decent place to develop most of the games that we're showing here are Unity games. There's only a handful of them that are native experiences. And this really does owe itself largely to this asynchronous time warp ability. And Qualcomm was the company that really stepped up and implemented this, where we had talked about it early on. I said, there's 2 things that I wanted from the GPU vendors, really. I wanted this context priority so I could do asynchronous time warp, and then I wanted a way to replicate effort between the 2 eyes to do stereoscopy with 1 pass through the driver. I'm already past my time, but maybe I'll get to that later. So Qualcomm basically went and they implemented Imagination Technologies extension there, but without the limitation of needing to be in multiple processes. So that allowed me to then run the time warp thread on its own GL context, and it synced to this 120 times a second left eye, right eye, going back and forth, running at the highest scheduling priority of any of the threads there. So it gets its within 1 millisecond scheduling. It batches up the graphics for that, and at some level in their driver, it interrupts something else and gets there. Now, in the ideal world, that would be perfect, and we would never, ever see a terror judder. But there's a couple of things that make this not quite perfect. There's a few things we know about, and there's a few things that we still don't completely understand. But the basic thing is it does work. It works as a win where I try to tell, people hear about this and they think, oh, it won't matter what I render at. And that's not true. You've got the lower your frame rate, when you've got things near you, they'll feel jerky. But it's the jerky feel of a computer game that needs an upgrade to the GPU. It's not the unbearable hell of jerky judder in DK2 where with the low persistence display where just everything is killing you with it. And the truth is, for a lot of things, you can drop a frame and not even notice that it happened. So I try to tell developers, this is frame rate insurance. This is not magic where you don't have to worry about performance, but work hard, try to get to 60 frames per second, try to do your best to stay there. But if you slip up a little bit, or if something else in the system glitches a little bit, then we can handle that and we can make a new frame kind of magically appear there. And it does still work where you can say, it is a 30 hertz experience, and we're going to double every other frame. It's definitely not as good. For certain things, it can be okay, and that's one of the things we're still debating for when you run into the thermal limits. Do we offer this option of just saying, well, we can knock the experience down to 30 frames per second, and that should run steady state at the lowest clock settings there. We're still not, we need more test cases to see whether that works out well or poorly for the different things. But still, it was a huge, huge win to get that asynchronous time warp working, and that's, I think, one of the big achievements of the last year. So we're trying to get that onto the PC for a lot of these things, because as we start looking at these things, 90 hertz displays, even 75 for DK2, these are hard to hit, even on the PC with all that horsepower. And I've said it many times before, and people don't like to hear it, but the PC costs about a factor of 2 in sort of the overhead that you wind up incurring when you're dealing with latency, not with bandwidth. The raw throughput, if you queue it all up, you got scads there. But if you're trying to do these very tight timing things like rendering to the front buffer, never dropping a frame, switching between there are challenges on the PC. So we are deeply engaged with NVIDIA, and we expect to. There's the whole matrix that we're going to have to work through. NVIDIA, AMD, Intel, and then PC, Mac, Linux. That's a lot of work to get some of this really twitchy stuff working. The work is ongoing right now, and there are varying levels of optimism and despair amongst different people in the company about how well this is actually going to work out on the PC. But I keep thinking it's the same thing, though. We need the existence proof. What we're probably going to wind up doing on this, if some magic doesn't happen in the coming days, is something that I actually tried on the cell phone first, was doing the time warp, the asynchronous time warp, on a CPU core. Burn an entire CPU core so it's just doing texture mapping like a horribly inefficient GPU, and have it schedule at the CPU level where we don't have this massive backlog of buffers going. And that actually worked on the cell phone, but it was one of those things that in a minute it overheated the cell phone. That was where it was just totally overdriving everything. But on a PC, we could actually do that. There's plenty of quad-core systems that really do have a core idle, and you can't then do the really fancy stuff like multiple composited overlay planes with deghosting going on, but you can do a chromatic aberration corrected time warp that can render right ahead of the raster. And once you start doing that, instead of just left eye, right eye, what we can do, we can turn this on even in the mobile, where you can go to the sliced rendering, where you cut each eye up into 4 slices. And then you can say, well, I am going to render just the slice ahead of me instead of the whole eye. So I've had Gear VR running actual applications with 4 milliseconds motion to photons time, where you've got a 2 millisecond window, some USB overhead, some scan out latency. But that doesn't work quite as well because of these. The other thing, the difference between theory and reality here is that having the high priority context extension doesn't mean that it happens right when we do it. There's still all these layers of buffering that have to happen. Some of them are kind of Qualcomm specific, and we have painful choices about how we can turn this one thing down, but it doubles the CPU overhead and command processing for things. And that's where we're at right now, where if you spend a lot of time in the applications that we've got for demos, you'll see some of them that occasionally have a little glitch, a judder or a tear line on the screen. And in fact, there's 2 different types of judders that you can notice if you're watching carefully. If you see a tear line mid-eye, that's because we somehow overshot our graphics cushion, which is a combination of both the CPU cushion and the GPU cushion. And the problem with that is, unlike like Imagination or Mali technology, where they're really tiny tiles, like 16 by 16 or something, the Qualcomm Adreno has fairly large tiles. It's a pretty good-sized block of memory on chip, and it might be a ninth or a 12th of the screen of the eye buffer or something. So it can be a decent-sized chunk. And they have to have at least a couple of these in flight to have decent efficiency. And then there's the question of how often they pass them off from the client application to their driver. So there's all these trade-off questions. So you can wind up with some things like there's some Unity applications that have some pretty heavyweight graphics rendering. And if they really throw a lot in and it all happens to wind up being in one tile, so we can wind up being some number of tiles behind. And if it turns out that you really more than doubled the amount of time we'd like you to have in there, we can still wind up blowing past that particular margin. And that happens on some apps right now. The other one is an interesting thing that that we only got to the bottom of recently. And this is something that people that aren't really involved with embedded display technology or probably aren't even aware of. But one of the new tricks that these ever-persistent people saving power on cell phones are doing is that the displays now are often smart, meaning that they are not just blindly DMAing pixels from memory and then putting them into charge cells or whatever on the display. They often now have a complete embedded frame buffer on the display. So the idea is that a lot of time you're looking at your cell phone, there's really not animation going on, and if they know from their compositor that, hey, we changed something, let's push one frame down, and then we don't touch it for seconds later, because the main memory is pretty expensive there, so that's an issue. But what that means is that even though I'm rendering to this front buffer, the display controller might not be being told every time that, hey, you still need to render to this. It's something that one aspect of the Android system software, normally it's managing the compositor and doing all this complicated stuff, but still for the VR apps, at least once per frame, it needs to wake up and say, hey, you need to get the next frame. And if it ever doesn't get that, then we miss an entire frame and you see a kind of like a DK2 style swap judder on things. And this is really unfortunate because we have our applications at these high real-time scheduling priorities, but Samsung is really scared to it's probably not a good idea to put some core part of Android at a scheduling priority where it could have priority inversion problems and different things like that. So we really want them to switch it back into a video mode, but they're all like, we're locked, we're shipping, this is a scary change, we don't want to do this right now. So it may be something that we live with for a while. But we all understand the issue now, and I'm confident in future versions that problem will go away. But there's still a few random, unexplained things that we can see. Some things, I think, dealing with audio that can cause us to glitch up. And this is something that we wish we had better yet visibility into the Android systems, but there's still a learning process. Again, a year ago I went into this knowing nothing about Android. I'm still far from an expert, but we know our way around a lot of this now, and we're getting what we need to accomplished. So I've pretty far shot over my time here. There's lots more to talk about, but I've got at least a little bit of time for some questions here. But I'm around all day, and I expect to completely lose my voice today. So a couple times already, just catch me anywhere. We can form a little crowd, and we can go over whatever topic you want. But if we can go ahead and I've got a few minutes. We can probably blow past the budget a little bit longer, but we've got a little bit of time for questions if you want to start lining up at the microphone. Or, okay, if you want to. Yeah. So brightness, the question about whether we want to have some overbrighting factor for the interlace like you would do on to compensate for it on TV sets. Brightness is an interesting question. In fact, to talk a little bit more about the actual display technologies there, currently Gear VR has an option, a brightness slider, and I'm not even sure that's really a good idea. One of the aspects is that our low persistence value is related to our brightness levels. When you're below a certain brightness, you're at 20% duty cycle, and when you're above that brightness, you're at 30% duty cycle. And I wish we were even lower, because 20% duty cycle in 16 milliseconds, that's 3.2 milliseconds, and DK2 runs lower than that. And when you get all the way up to 4.8 milliseconds, it's getting to feel smeary again. It's still 3 times better than DK1 or a full persistence display, but it's not great. So I would argue that And especially since if you've got all light blocked out from the display, I don't think you need a brightness selection. I think everybody sees the same things and you adapt to it fairly quickly. So I think a fixed display brightness probably would be a good thing. And if we control it directly, then we could pump up whatever we needed for doing that. But I don't think we would actually adjust it for interlace. I think that we would pick one of the values there and we would take whatever it gets. But the other aspect related to displays there is the color calibration, where the displays are color calibrated. Okay, I'm going to go on for a while about a few more of these display topics. So one of the things talking about resolution, so these panels are diamond pixel or pentile displays, which is generally not what you want. You want RGB triad. You want to say, this is my red, this is my green, this is my blue. But these panels, they wind up, all the greens are there, but only half of the reds and half of the blues. When I first hear about this, each time I think, oh, they're just cheating. They want to be able to claim they're a 1080p or a 1440p display without actually having all of those pixels. But it turns out there is another more significant reason, especially with OLEDs. The blue OLEDs will burn out quicker if they're the same size, so making them larger and driving them lower is a positive thing there. But this does mean that for the graphic techs that get really high-end obsessive about filter kernels and things like that, you have to know that whatever you push out on red and blue is not going to be what winds up on the display. It's going to be a function of 2 to 4 of the surrounding pixels there. I was pleasantly surprised to find out they actually are gamma correct. I had just assumed that it was going to be busted and done in linear space, but it's gamma correct, and the calibration on them is actually, it's much better sRGB calibration than on my desktop monitor. There's still a little bit of room for improvement. The top saturates a little bit more, and the bottom ones aren't quite right. And in VR, the linear ramp on sRGB is a terrible thing that we might be better off not being sRGB. But we've got good quality on a lot of that stuff. But the other little thing that I would mention to game designers and interface side of that is there's a consequence of that fact that we've got twice as many greens as reds or blues. If you really care about information and conveying something like text, there's a good argument to be made for doing it green on black. Pick a matrix style there, and or it's like an 80s Apple II monitor, where that will actually be the crispest, most legible way of doing things. And one of the clever things that our UI guys puked at the idea of green displays, so they at least came up with the kind of clever idea of having a very subtle green outline around things, so it still gives kind of the crisply defined outline, just with a little hint of green around it. But just going green on black would be the way to really convey the absolute most information. Yeah.
Hi, John. Thanks for coming out here.
Yeah.
I know it's a long flight. So you said Brendan likes to think about the sit-down experience, the sit-down VR experience. Well, I'm more about the stand-up experience, full-body VR. I know the data you get from this is pretty coarse, but do you think that there's any value in taking data from, say, GPS or a pedometer to track movement, like walking around? Is Oculus even thinking about that? So
the thing that keeps coming up that gets overlooked so much is sub-millimeter precision for the tracking. So the question of whether we can use larger scale things, although some GPS is amazing technology. I mean, some of the real-time kinematic GPS stuff is giving millimeter level accuracy from things, usually not in real time, but that is startlingly close. I'm getting the please wrap up angry message here. Let's try and let's clear the people that are at the microphones here. So no, I don't think that we've got any near-term plans for that. In the long term, in our world of VR and AR, then yes, that will be used at some point. Let's go ahead.
Just related to movement tracking, like Google's Project Tango. Have you guys got?
Yeah, we had the Tango demo and everything.
Yeah. So how accurate was that in terms of?
So it was better than a lot of people expected, and yeah, you could look around, and it's not sub-millimeter, but it's like a heck of a lot better than what most AR toolkit type things are going on. And they have they've got their structured light sensor that they can use for extra fixes. As I understand it, they're still doing most of it through the standard camera experience, though. So it's great to see all of this work coming on, and I'll be happy if somebody else nails this problem through cell phone cameras, I'll be thrilled. It'll be one less thing that I have to kind of work on in the different things. So,
do you know off the top of your head what the latency and positional?
I don't know what it was, but that's actually not that important. That's something that's not immediately obvious. But all of these systems, all of the VR systems on this use the IMU for all the up-to-date stuff. It's a matter of they just need to know at some point in the past, not too far in the past, then you can go ahead and say, this is where you really were, and then reproject through. So if it's even 100 milliseconds, ideally less than that, but you can have a pretty long latency. As long as you know what the time was, you can recorrect from there, and it doesn't have to be, because you don't get it, there's nothing that we've got that delivers everything right now. We want 2 milliseconds latency, and you're not getting that from an optical system, in consumer gear at least.
Thank you.
Yeah.
You did mention that you were getting the camera pass-through on the Gear VR, like
Yeah.
Keynote 4. Have you guys been doing any augmented reality kind of applications or work with the computer vision coming out of that, not just for position tracking?
Okay, so if anybody's going to do an augmented reality application, you must not stretch the camera larger than what it is, where the camera on the Gear VR is a 60 by 45, like 60 by 45, something like that degree, which is this small area in VR. And you could go do an AR experience with that. And we've got the 120 hertz camera, so it's way better for doing that than any kind of standard AR experience using the 30 hertz camera interface. But I see lots of people then go ahead and take that camera and say, I want it to be big, and stretch it over everything, which then becomes far worse than any sin we've ever committed in any of our distortion calibration stuff. You don't just stretch it up over like that. So there's some work that's been done on them. I haven't seen anything that... I'm not a big fan of AR cell phone applications. Really, I've seen a lot of demos, and I think that they are technologies looking for a product, looking for a reason to exist. I've played with a bunch of them, and I am yet to be won over. It may just be a matter of that the quality is not good enough, that it needs to be 60 hertz with a 120 hertz scanner, updating all the time, not dropping and popping and having all the different problems. If augmented reality with sub-millimeter precision and no jitter with low persistence might be a very cool thing, but I've yet to see it.
Hi there. Irrespective of the resolution or the pixel density, the size of the device and the screen actually, do you feel the current size for the Note 4 is a good one? Smaller or larger would be better from the trade-offs with weight? How do you feel about that?
It is remarkably close to optimal. It is, it's very close to twice the average IPD for people. It's about where you'd want the interaxial for the lenses. We waste a little bit of display off the top and bottom with the current lenses. One of the big things that I want to push for is non-circular lenses, where ideally we would have lenses shaped to project an image that's the full, we're rendering a square image in software, and then we're throwing away the corners of it by the shape of things. So I think it's actually a pretty darn good trade-off. I mean, obviously, it would be better if we had separate cantable, interaxial, adjustable displays, but if it's going to be one display, it's almost perfect in size.
Thanks.
I mean, I guess unless they literally chase me off the stage, I can stay here answering questions until they...
Hi, John.
Yeah.
We actually are going to end for lunch.
Okay.
And if we can just take the rest of the questions offline, that would be
All
great.
right.
Thank you.
Thanks, everyone.